Myself Rakshit. Today I am going to explain you about our project, recent advances in modeling, simulation and implementation of novel control schemes for power quality improvement using AI, ML and ANN approaches. The project is all about improving the power quality by verifying the problems such as voltage sags well and helping and rectifying them. First, we are doing a MATLAB Simulink model in order to explain our project. First, open the MATLAB. Next, have to go to the Simulink section here. Next, I am going to explain. I am going to open my R files. Here, now the files are open. I have opened two files. One is with UPQC and one is without UPQC. UPQC is nothing but unified power quality conditioners, which help in helping voltage and current imbalances. The first one here is the one without UPQC. Here you can see there is a source. Here we have given like 400 volts, 50 hertz, so three-phase voltage. Here this is a three-phase VI measurement, which is used to measure the voltages, and then here is the common line inductor, RL inductor, and then this is the bridge rectifier, and this is the RL load, that is nothing but the non-linear load, which depicts our houses. After we open the file, you have to press here. You can see on the top there is a run button. You have to press it. Now after pressing the run button, you can see there is a block called a scope here, where you can see the waveforms. When I press the scope, you can see voltage sag and voltage swell have been shown. Since it is without UPQC, you can see all these. That was voltage waveform. Now I am going to show you about the current waveforms. Here same, you can see the three-phase current waveforms with sag and swell. Next, you can see the RL load. Here I have given the resistance as 100 ohms and inductors as 0.5 millihenry. You can give any value for this, and then here you can see a block called power GI. It is nothing but it is used to find out the total harmonic distortion. Here when I click power GI, you can see there's a window. You have to go there and press FFT analysis. When you enter FFT analysis, you can see the waveform. Here you have to go and select, and then select any waveforms and then show display. You can see the total harmonic distortion is 34.54%. Next I am going to select for the voltage one. For the voltage it is 20.42%. Now you have seen the one without UPQC. I'll be showing you about how we have implemented the UPQC, and then show you the total harmonic distortion. Now I opened the file with UPQC. Like the old file, you have to come here and press the run button above, and you have to wait for a few minutes. Now you can see once the program is in, you can see this UPQC block. It is attached to the previous model. The UPQC is nothing but it consists of a series filter and a shunt filter, along with a DC link. DC link is nothing but the capacitor here. Now we are given a photovoltaic and boost converter, which is used to generate the compensation for the extra voltage which has been lost due to the harmonics. And then here you can see the power factor measurements where the power factor is measured. Similarly, like last one, here we've given the voltages 440 volts and 50 volts for the three-phase voltage, and then you can measure the three-phase VI measurement use a block, and then this is the scope for the voltage and this is the scope for the current. Now when we come to the series filter is mainly which is used to for voltage related rectify voltage related problems. It consists of many IGBTs, and then what we have used here, what we have used is a 27 level multi-level inverter. Actually, when you talk about a multi-level inverter, there are actually two types. One is the common DC source and the separate DC source types. What we have used here is a cascaded H-bridge multi-level inverter. Here we can see a reference voltage calculation block where VA is nothing but the input single phase voltage block, which is given as input for this, and then there's a relay, and then all these are provided given to the IGBTs. Then comes the shunt active power filter. The main aim of shunt active power filter is to rectify the current related problems. The active power filter, it overcomes the drawbacks of the passive power filter by using the switching mode power converter to perform the harmonic current elimination. The shunt APF is mainly made up of PQI compensation calculator, hysteresis controller, series filter, and a PI controller. Actually, the shunt, it is actually based on an instantaneous reactive power theory. When when you press the PQI compensation calculator block, here you can see there are many blocks. This VABC is nothing but three-phase voltage, and IABC is nothing but the three-phase current, which has been given to the Clark V and Clark I, which are nothing but the Clark transformation blocks. These Clark transformation, what they do is they convert the three-phase into single individual blocks, individual currents. Like x1 and x2, you can see PQ calculation. See, it is nothing but P and Q are the active power and the active and reactive power, P and Q. Next, it is given to a Butterworth low pass filter. This Butterworth low pass filter is a fifth order. In order to get a smooth output, we are using a fifth order Butterworth filter, low pass filter. Here, instead of using a low pass filter and then some, you could have used for a high pass filter, but in practical cases, designing a high pass filter and using it is very it's not a good idea. So we have used a Butterworth filter, and then we have subtracted it with PDC. Here, as we all know, power, it is made up of DC and AC components. So when we use a low pass filter, we are only going to get, it will eliminate the AC component, and we are going to get the DC component. And here we are getting PAC plus PDC. So when we subtract it, we are going to get a negative of PAC components. Hence, and then here you can see the loss has been given to a neural network block, which are all been given to alpha beta current block. Here, P oscillation, you are going to get the individual currents, IC1 and IC2, which are then which you can see it in the scope. This is the current waveform. You can see at the beginning there were a lot of irregularities, but you can see the regularity laterwards. then which is, it is given to a compensation current. Here the peak the Clark transformation currents IC1 and IC2 have been again converted back into single phase currents ICA, ICP and ICC, which are again given to a mux in order to get all three waveforms at once. And then you can see ICABC. ICABC is nothing but the three phase current. That three phase current is given to a hysteresis controller. Hysteresis controller is it is used for the generation of the PWM signals, which are used as a gate. It is used to as a control for the gate of inverters of the transistors. Which you can see G1 and G2. These are the gate pulses which have been given to the series filter. And then here you can see, as you all know, the series filter is made up of a 27 level multi-level inverter. And then in order to control this, you are going to give the gate currents, and then you are going to get output N1, which is given to a PI controller. What PI controller does is it compares the output with the reference input which is given to it, and then calculates the power loss, and then the power loss is again given back to the PQI compensation in order to compensate for the lost power. And then when you come back, you can see the line RL line, right, for which we have given as 0.6 ohms and 10 power minus 3 Henry. Here we have just given as a random value. You can give any value, but what we have followed here is for per kilometer there's always 0.25 ohms of resistance in a transmission line, so we have given as 0.6. And then here you can see the coupling inductors which connect that shunt APF with the transmission lines. And then here you can see a diode with RL load, which is nothing but a non-linear load. And then now I'm going to press with the power GUI and go to FFT analysis, where you can see the total harmonic distortion. Now I'm going to see what the current. See, previously we had somewhere around 30%. Now the total harmonic distortion have been reduced to 8.55%, which is a very great improvement. And then we are going to see the voltage of it. Voltage total harmonic distortion. See, the voltage total harmonic distortion is around 7%. Whereas it was 22%. So you can see great improvement in total harmonic distortion. This was our project. Thank you.